in AvalancheJS Summer 2022 Workshop Day 2. Today, we have two sessions brought through by engineers from Ava Labs. They will going to be helpful for your project submissions as we kind of move along as well. Before we begin for today's session, first of all, I'd like to thank all the sponsors for AvalancheJS Summer 2022, namely the Graph Foundation, QuickNote, and Certic, who have actually contributed to the bounties of the hackathon as well. So a quick overview of what the hackathon essentially it's about. This hackathon focuses on the disruptive technologies such as GameFi and DeFi, which has been gaining momentum in the Web3 scene. And for the hackathon, it's really for all participants to really be focused on solving challenges in these two key areas using Avalanche. So this hackathon has two main tracks. First of all, will be the DeFi track, where we'd like you to utilize Avalanche to create DeFi dApps, tooling, and infrastructure in order to attract and onboard the next wave of DeFi users into the ecosystem as well. Of course, the next track, which is GameFi, really focuses on leveraging the power of Avalanche to create or explore new mechanisms for Web 3.0 gaming to create a fun and interactive experience for gamers. Of course, the submission does not have to be a game, essentially. You can really focus on various elements of gaming ecosystem as part of your project submissions. With the sponsors, they have also contributed to the bounties, which you can leverage onto your main track submissions that you are building for the hackathon itself. There are 4 bounties out there ranging from 1,000 to 1,500 price that is contributed to the prize pool as well. So this hackathon has over $55,000 in prize pool that's up for grabs. Really encourage you to kind of explore what you can actually leverage Avalanche for in terms of DeFi and GameFi as you kind of work through with us for the next 3.5 weeks essentially as well. One key thing to kind of bring up to everyone here is that regardless of the complexity of your ideas, here in AvalancheJS Summer 2022, we really would like to encourage all of you to actually submit the project and just feel encouraged and empowered to kind of build the next big thing for the ecosystem as well. So before I pass the time to our first speaker, Gabriel, for today, just a quick reminder for those joining us on Zoom or live on AngelHack YouTube channel. If you have any questions for any of our speakers with regards to the content of their workshop, please feel free to drop into either the Q&A box or the live chat on YouTube itself, and we'll get to them towards the end of each of the sharing session as well. So please feel free to drop any questions that you have to help you understand further, especially on the topics that's being shared today. So first up, Gabriel, Senior Test Engineer and Developer Evangelist from Ava Labs, will be covering Avalanche JS. Gabriel, the time is yours.
Thank you so much, Justin. Can you hear me okay?
Yep, all clear.
Okay, excellent. Okay, I'm going to share my screen. Yes, and as Justin mentioned, we're going to be doing questions and answers towards the end. So if you have any questions, please drop them into the box here on Zoom or on YouTube. And as he mentioned, they'll get aggregated. Justin, feel free to cut me off at any time when you're ready to transition to the Q&A portion of the presentation. So thank you so much. Again, we're going to go ahead and get started. My name is Gabriel Cardona, and I'm Developer Evangelist at Ava Labs. Today, I will be presenting you with an introduction to Avalanche and with a focus on Avalanche JS. So it's going to be a high-level introduction to the Avalanche network. We're going to talk about who we are at Ava Labs and what we've been building over the last couple of years. We're going to dig into a few of the unique attributes of the Avalanche network, which are namely Avalanche Consensus, Subnets, and virtual machines. And then lastly, we'll focus on Avalanche JS. So let's go ahead and get started. So who is Ava Labs? We are a world-class team of experts in the fields of computer science, economics, law, and finance. Our offices are located in New York City and Miami, but we have team members spread all over the world. So I am personally located with a handful of other teammates in the San Francisco Bay Area, which is where I'm coming to you nice and early, 5 a.m. this morning. So good morning to everybody on the West Coast. And I believe that we have team members on every single continent other than Antarctica. So we are genuinely a worldwide team. We're passionate individuals with a vision to create a frictionless world by redefining the way that people build and use finance applications. The Ava Labs team has collective experience from leading Fortune 500 finance and tech companies through to high growth blockchain companies. And here are some of the companies that my amazing teammates were at prior to joining Ava Labs. I myself was at Bitcoin.com, which you can see on the bottom row at the right, where I was actually the global director of developer services prior to joining Ava Labs. And I've been working in the blockchain space for quite a few years now. And I genuinely believe that Ava Labs and the Avalanche network are very, very important milestones in this entire blockchain journey. And so I'm very glad and honored to be here today sharing with you. Here is our C-level suite. Pardon me. So at the top is our CEO and one of the co-founders, Professor Amin Gun Sarir. He was a professor at Cornell for over 20 years. And one of his many, many claims to fame is that he was actually the creator of one of the very first virtual currencies for peer-to-peer systems, which used proof of work. And this system was called Karma, and it was created way back with him and his team in 2003. So 5 years before Satoshi released Bitcoin, Gun and his team at Cornell were already solving problems in this space. Below Gun, on the left is our president, John Wu. John attended Harvard and Cornell and was previously the co-founder of Sego and Shoreview Capital. On the top right, we have our chief operating officer and co-founder, Kevin Seknicki. Kevin is a PhD from Cornell and was previously at Microsoft and at NASA. And then lastly, on the bottom right is our chief protocol officer and another one of our co-founders, Ted Yin. Ted is also a PhD from Cornell, and he was actually one of the creators of Hot Stuff. And Hot Stuff is the classical consensus protocol, which is behind Facebook's Libra or DM network. And now he is at Ava Labs, working on Avalanche Consensus and many other exciting protocols. Very briefly, who am I? So as I mentioned, my name is Gabriel Cardona, and I'm a developer evangelist at Ava Labs, where I lead our developer relations squad. And the developer relations squad has really three main functions. First off, we maintain AvalancheJS, which is our TypeScript JavaScript library. We're going to talk more about that today. Next, we do partner integrations. So we spend a lot of our time on Slack and Telegram and Discord, helping new teams and companies understand our technology stack and understand how to integrate it with their existing technology stacks. And then lastly, I also go around to conferences and conventions and hackathons and meetups, and I give presentations like I am this morning, hoping to inspire people to build amazing applications on the Avalanche network. I genuinely believe that there is no more valuable resource on the entire planet at this moment in time. There's nothing more valuable than a competent, hardworking, and a creative engineer. And I feel that way because I think we're at a unique time in the evolution of our species where we really need to solve problems at scale and velocity. And fortunately for us, there have been so many radical breakthroughs in computer science over the last 200 years or so. So if you go all the way back to Ada Lovelace and Charles Babbage with his difference and his analytical engines through till today, there have been so many radical breakthroughs that we have a tool set which is unlike any time in all of human history. So now we just need hardworking and competent and creative people to step forward and to build the systems which are going to solve the problems. And so I often say there's never been a better time in all of human history to have a great idea, find a group of like-minded people, raise capital, change the world in a radical way, and uplift the human condition. And so hopefully I can inspire somebody who's listening today to build their game-changing idea, and hopefully, ideally, you will build it on the Avalanche network. And of course, we are hiring. So if you're in the field of computer science, economics, law, and/or finance, and anything that I talk about today excites you, please feel to reach out to me personally, or you can check out avalabs.org/careers. We are hiring across the board in biz dev, engineering, marketing, operations, product, security, design, and more. So please feel free to check out avalabs.org/careers or reach out to me. My contacts will be on the very last slide if we make it that far. Okay, let's go ahead and dig into this now. So what is Avalanche? Avalanche is a global financial network for the issuing and trading of all digital goods. And we enable potentially millions of validators to process thousands of transactions per second with near instant finality using a protocol which is completely green and quiescent. And we've paired this high throughput and fast finality protocol with an architecture that can meet the needs of unique financial services and decentralized applications. And we accomplish this through this notion of subnets or subnetworks. Subnets allow anyone, anywhere, to spin up a tailor-made network with custom virtual machines and complex validator rule sets, both of which we're going to dig into. So Avalanche is a network of networks. It is a platform of platforms, and we envision thousands and thousands of these public and private subnetworks all emerging into this global marketplace, which we call the Internet of Finance. So before we start, I want to give a brief history on the evolution of the blockchain revolution. And I suspect that most of the information on these next few slides won't be news to some of the people watching today, but I have found that to truly appreciate where you're going or where you're headed, it helps to truly understand where you're coming from. So very briefly, let's give a history on the evolution of the blockchain revolution. So blockchain 1.0 was Bitcoin. And in the beginning was Bitcoin, and Bitcoin was good. And Bitcoin proved to the world there was the need for a robust and a decentralized payment network. It started its life out as peer-to-peer electronic cash, but for better or worse, that's not ultimately what it grew into. Now it's much more akin to digital gold. And there was a while, I've been in the blockchain for many years. I got my very first Bitcoin in 2011. So I've seen this journey. I've been through all of these chapters. And there was a while when I was a little bit salty about Bitcoin not emerging into peer-to-peer electronic cash for the planet. I thought that was a very, very powerful vision. But over the last decade, I've matured a lot. And of course, my viewpoint has changed. And now I appreciate that Bitcoin has grown into a hedge against inflation for mom and pop investors. So very briefly, what is inflation? In economics, inflation is a general increase in the prices of goods and services in an economy. And what are the long-term impacts and effects of inflation? When the general price level rises, each unit of currency buys fewer goods and services. So consequently, inflation corresponds to a reduction in the purchasing power of money. And so I see inflation as a silent form of theft. And some people argue that taxation is theft. However, with taxation, at least you can point to some of the common utilities and infrastructure which we all depend upon, such as, the roads or the police or the military. And we can say, well, that is what our taxes are used for, and we all benefit from that. But with inflation, your purchasing power is simply going down continuously, and there's nothing that you can point to in return. And so sort of a shocking figure is that 1 out of 5 US dollars that have ever been printed in the entire history of the United States were printed in 2020. So let me say that again. 1 out of every $5 that have ever been printed in the entire history of the United States were printed in the year 2020. So consequently, the purchasing power of every single person listening today of their US dollar has decreased by about 20% or so over the last couple of years. And that trend is going to accelerate. And I certainly feel it. I live in the San Francisco Bay Area, where everything from my rent, my bills, my groceries, my gas, everything has either increased in price or decreased in quantity. And this is potentially the beginning of what hyperinflation looks like. And, I don't want to be hyperbolic, but if you don't think that hyperinflation can happen in the United States, check out Zimbabwe, check out Greece, Venezuela, Argentina, etc. There are many countries where hyperinflation has in fact happened. And Bitcoin and other cryptos such as Avax, they allow you to opt out of inflation. And trust me, your kids and future generations will thank you for that. So as big of a leap forward as Bitcoin was, and it was huge, it turned the entire financial industry on its ear, it still has its downsides. So namely, Bitcoin is slow. It only does a handful of transactions per second. It doesn't have fast finality. It takes about an hour before you can be confident that your transaction will not be reorged out from under you. It's not lightweight and green. We all know the meme about Bitcoin burning more energy each day than some nation states. Though for what it's worth, I view that only as a short-term problem. I believe the entire planet is going to transition into renewable energy, and that will happen within our lifetime, because necessity is the mother of invention, and there is a need right now to transition to renewable energy. Every single hour, enough energy falls on the planet in the form of sunlight to meet over 100% of our yearly needs, including fossil fuels, renewables, and nuclear. So really the problem is about harvesting this energy, storing it, and transporting it. And these are all problems which I believe will be solved in our lifetime. So I think the idea that Bitcoin burns a ton of energy, I believe that is a short-term problem only, but it is a short-term problem. It's bad optics. You often see headlines that say, crypto is even worse for the environment than you thought. And they're almost always referring to what I'm talking about here, which is that Bitcoin's proof of work burns more energy than some nation states. Furthermore, Bitcoin has a scripting language. It's creatively named Script, but it's very archaic and cumbersome to use. It's stack-based, and it doesn't feel modern for someone who has come of age in the era of Golang, TypeScript, Python, the modern web. And lastly, Bitcoin doesn't really have tokens. So technically, there is an opcode called OP_RETURN, and it enables you to write 80 bytes of arbitrary data to the blockchain, which can be used to encode asset creation, minting, and transferring and burning commands. You can then write wallets which can tease out those 80 bytes, decode them, from which you can have tokens, but it's really a technical hack, and the tokens are not native to the Bitcoin virtual machine. So in summary, Bitcoin was a huge leap forward, and it kicked off a financial revolution, but it left a few things to be desired, and it inspired engineers to try and do better. So very quickly, I just also want to say that Bitcoin had a radical impact on the lives of many people, myself included. So as I mentioned, in 2011, I got my first Bitcoin, and I fell down the Bitcoin rabbit hole, the crypto and Bitcoin rabbit hole, and I suspect I will never emerge. I've been working in this career ever since, and it's changed my life in such a radical way. It taught me about technology, it taught me about money, it taught me about social dynamics, it taught me so much more. So I always like to just express gratitude to Satoshi, and express that my wish is that he or she or they or it, whatever Satoshi happened to be, I hope they're out there living their best life. And I hope that they're happy and healthy, and that they're working on the next generation of amazing technology. So if you happen to see this, Satoshi, thank you so much for everything you've done for everybody. Next, we have blockchain 2.0, and we think of blockchain 2.0 as Ethereum. And so Ethereum is a decentralized application which enabled developers to launch their own dApps on top of it in the form of a smart contract. And prior to Ethereum, if you wanted to launch your own dApp, then you had to roll your own network. And this led to a very bespoke environment where very few projects were able to reach the network effects required to tip and go mainstream. And so by enabling developers to launch their dApps on top of Ethereum, it enabled a huge network effect that led to a huge wave of innovation around tokenomics, initial coin offerings, non-fungible tokens or NFTs, decentralized finance or DeFi, yield farming, prediction markets, distributed autonomous organizations or DAOs, and so much more. So I remain a huge fan of Vitalik and his team. I think Vitalik is one of the great thinkers of our age, and he's still a young man. I think he's in his early 30s. And I'm a big believer in life extension. So to me, 30 is like the new 50, or I'm sorry, 50 is the new 30, I should say. So 30 is very, very young, in my opinion. And so I suspect his best days are still ahead of him. And the analogy I like to use is Linus Torvalds. So Linus Torvalds famously created Linux, and I think of that at his chapter 1. And then he came back, and with his chapter 2, he created Git. And so I'm always interested to consider what Vitalik might do after Ethereum for his chapter 2, because as I said, I think of him as a very young man, and his best days are probably still ahead of him. So that was blockchain 1.0 and 2.0. We view Avalanche as blockchain 3.0 technology. It's a huge paradigm shift, and similar to Bitcoin and Ethereum, we are introducing a handful of new paradigms, which we are going to discuss today. We're going to discuss how Avalanche Consensus is the third major paradigm over 40 years in the field of consensus. We'll discuss how Avalanche is unlike most other existing blockchains, in that it's a network of networks instead of a single virtual machine and set of validators. And then we'll also dig into virtual machines, what they are, how they fit into the Avalanche network. And then lastly, we'll discuss how Avalanche enables developers to spin up their own tailor-made network with custom virtual machines and complex validator rule sets. Okay, so first off, what is consensus? If you work in the blockchain space, you probably hear the word consensus a dozen times each day, but what exactly is consensus? Consensus is the process by which a group of independent validators come into agreement on a decision. So it's really that simple. How do you get a bunch of people or machines to agree on a decision? That's consensus. And it's a very rich field of computer science that goes back at least 40 years. And as I mentioned, Avalanche Consensus is the third major paradigm in the field of consensus. The first, you can see on this comparison chart on the left, was called classical consensus, and it goes back to the 70s and the 80s. And classical consensus has low latency and very high throughput. It's lightweight and it's green. However, it isn't very scalable nor robust, and it performs poorly in adversarial conditions. In 2008, 2009, when Satoshi Nakamoto released Bitcoin to the world, we were all introduced to the second major paradigm in the field of consensus, what ultimately became known as Nakamoto Consensus. And Nakamoto Consensus is very scalable and robust. It's very decentralized, but it does not have low latency. As I mentioned, it takes around an hour to be sure your transaction is sufficiently settled that you won't experience a reorg. It doesn't have high throughput. Bitcoin only does a handful of transactions per second. Of course, I am aware of second layer solutions such as the Lightning Network. So just to be clear, I'm referring to the actual layer 1 Bitcoin protocol and network here. Bitcoin is not lightweight and green. As I mentioned, it burns more energy each day than some nation states. And lastly, Nakamoto Consensus performs okay in adversarial conditions up to the famous 51% attack. In 2018, a pseudonymous group going by the name Team Rocket released a white paper on the Interplanetary File System, or the IPFS, describing a third major paradigm shift in the field of consensus. This new breakthrough was known as Avalanche Consensus. And Avalanche Consensus is really the perfect storm of features from classical and Nakamoto Consensus. It's very scalable, very robust and decentralized. There are currently, I don't know the exact number, it was up to 1,500. It might be a little bit below that or above that. I haven't checked in a couple of weeks, but let's say 1,500 because that was what it was last time I checked. So there are currently around 1,500 full block and vertex producing validators on the Avalanche network. And the protocol theoretically enables millions of validators. So it's very, very decentralized. And Avalanche Consensus has low latency with sub-second immutable and irreversible finality. So there is no notion of a reorg attack on Avalanche. That's just not even a concept that exists in the context of Avalanche Consensus. So within a literal blink of a human eye, your transaction has completely settled immutably and irreversibly. That's very, very exciting and opens up an entire class of problems to be solved, which were frankly not able to be solved when you need to wait even 20 seconds up to an hour for your transaction to settle. Avalanche has high throughput with 4,500 transactions per second. It's very lightweight and green and can be run on a PC. It can be run on a MacBook. It can be run on a VPS, drop it on the cloud. And in the future, it will be able to run on Internet of Things devices. And Avalanche Consensus is parameterizable, so it performs very well in adversarial conditions. And I have this demo. Sometimes it works, sometimes it doesn't. Let's give it a little shot here. So is it going to work? It is. Excellent. So very quickly, before we show it. So technically, Avalanche is a metastable consensus protocol inspired by epidemic protocols and gossip networks. The process used to determine whether a transaction is preferred or not is referred to as repeated random subsampling. Excuse me. I'll repeat that. The process used to determine whether a transaction is preferred or not is referred to as repeated random subsampling. And here is a great demo. It was created by our Chief Protocol Officer, Ted Yin. As I mentioned, Ted was one of the creators of Hot Stuff, which is the classical consensus protocol behind Facebook's Libra or DM network. He's now at Ava Labs working on Avalanche Consensus. So what you're about to see in this demo, you can see the squares at the top. These squares represent different nodes in the network, and the color of each square represents its current proposal. So this square is saying, is this transaction blue or is this transaction orange? And it's worth noting that Avalanche Consensus can handle non-binary decisions. So for example, you can give it 5 options instead of 2, and it will still reach immutable and irreversible consensus. But for the sake of this demo, and in most transaction-related decisions, we're going with a binary decision. Is it blue or is it orange? Is it accepted or is it rejected? And the darkness of color shows the node's conviction in that proposal. So does this node kind of think the decision is blue, or does it really, really believe that the decision is blue? So when I click start, each node will begin repeatedly and randomly sampling its peers and changing its own color and conviction based on the responses that it gets back from its peers. And expectedly, all nodes will collapse to the same color in the end. So here we go. You can see that it only takes a couple of rounds of sampling and the entire set will actually tip and avalanche into consensus. So let me play that again because it's really beautiful. So again, you can see that it only takes a couple of rounds of repeated random subsampling and the entire set will tip and avalanche into consensus. So hopefully this gives you a bit of an intuition around how Avalanche Consensus works. Repeated random subsampling. Okay, so that's Avalanche Consensus, which is the third major paradigm shift in the field of consensus. Next, let's discuss how Avalanche is a network of networks. As I mentioned, Avalanche is different than traditional crypto networks like Bitcoin and Ethereum that have one virtual machine and one set of miners or validators. Avalanche is a network of networks with compound network effects. And I have this really great slide to help visualize this. Credit and shout out to the amazing CryptoSec. You can see their Twitter handle is at the bottom right of the screen. Please go follow them on Twitter and check out their Medium account for some incredibly deep and insightful posts about the blockchain, not just Avalanche, but the blockchain industry in general. Thank you so much, CryptoSec, an absolute block star. So here you can see that the gray oval represents the Avalanche network. And within the network are many different subnets or subnetworks, which are represented by the different circles. In each of those subnets are green squares, which represent the different virtual machines or blockchains that are running in those subnets. And the lines between the subnets show that you can move assets and users between the different subnets. At the top, you can see Bitcoin, Ethereum, and Cosmos with lines representing the ability to bridge assets from those other networks into the Avalanche network. And currently, bridge.avox.network supports bridging assets from Ethereum into Avalanche. And we recently announced that Bitcoin support is live as well. And so you can actually bridge both Bitcoin and Ethereum from their native networks into the Avalanche network so that you can leverage DeFi. And this number is actually a little bit dated, so I know this is much larger because it's been a couple months since I drew this number, but a couple months ago, there had already been 300,000 transactions and over 50 billion US dollars in ERC20 assets, which had been bridged back and forth between Ethereum and Avalanche. And then Bitcoin has also been incredibly successful since it went live a couple months ago. So absolutely huge numbers. Again, over $50 billion in USD in ERC20 tokens have been bridged between Ethereum and Avalanche. And that's actually an old number. I'm sure it's much larger than that now. And so I often say that Avalanche's subnet architecture is primed for compound network effects. And what exactly do I mean by that? Well, most people have heard of network effects, which technically are known as Metcalfe's law. So Metcalfe's law says that a network's value is proportional to the square of the number of nodes on the network. So for example, if a network has 10 nodes, its inherent value is 100. 10 times 10 equals 100. In other words, a product or service gains additional value as more people use it. And a great example of a network effect is the telephone network. If only one person has a telephone, then it's not very useful. For every additional person who plugs into the telephone network, then the entire network grows in value for every other user, I should say. And perhaps the canonical example of network effect is money. If only one person accepts a currency, then it's not very useful. For each additional person that accepts the currency, then it becomes more valuable for every other user who can then use their currency for goods and services. And we witnessed this with cryptocurrency, right? When Bitcoin first came out, and not many people used it, and a lot of people laughed at it pejoratively, it wasn't that valuable. But as more and more services and more people have accepted it for goods and services, the value of Bitcoin has gone up in value, not just from a USD perspective, but from a practical perspective of being able to spend your crypto on goods and services. So again, the canonical example of a network effect is money. But that's a network effect. But what about compound network effects? Compound network effects are known as Reed's law. And Reed's law states that the utility of large networks, particularly social networks, can scale exponentially with the size of the network, as the number of possible subgroups grows much more rapidly than either the number of participants or the number of possible pair connections. So even if the utility of groups available to be joined is very small on a per group basis, eventually the network effect of potential group membership can dominate the overall economics of the system. So this is compound network effects. They're basically ramped up network effects, and Avalanche's subnets are designed and primed for compound network effects. Next, we have virtual machines. So a virtual machine defines the application level logic of a blockchain. In technical terms, it specifies the blockchain's state transition function, transactions, and the API through which users can interact with a blockchain. And every blockchain on Avalanche is an instance of a virtual machine. The way to think about a virtual machine is like a class in object-oriented programming. A class is a description of an object. It's a template from which you can instantiate as many objects as you wish. And each of these objects, though derived from a common template, are unique and logically separate entities with their own state. So similar to a class, a virtual machine is a blueprint or a template from which you can instantiate as many different instances of a blockchain as you wish. And each of these blockchains, though they have been derived from a common template, are unique and logically separate entities with their own state. As a developer, when you write your virtual machine, you don't need to concern yourself with lower level logic like networking, consensus, or the structure of your blockchain. Avalanche does all of this behind the scenes so that you can focus on the thing that you want to build. You can focus on the special sauce of your application and let Avalanche handle all of the lower level networking, consensus, structure of the blockchain, etc. behind the scenes for you. And so why virtual machines? At first, blockchain networks had one virtual machine with a predefined static set of functionality, and this rigid monolithic design limited what blockchain-based applications one could run on such a network. People who wanted custom decentralized applications had to create their own entirely new blockchain from scratch. Doing so required a great deal of time and effort, offered limited security, and generally resulted in a bespoke, fragile blockchain that never got off the ground and never achieved the network effects required to tip and go mainstream. As mentioned before, Ethereum made a huge step forward solving this problem with smart contracts, so the developers didn't need to worry about networking and consensus, but creating decentralized applications still remains hard. The Ethereum virtual machine has low performance and imposes restrictions on smart contract developers. Solidity and Viper and the other few languages for writing Ethereum smart contracts are unfamiliar to most programmers. They're not very expressive and they don't fit into the rest of your development workflow. Avalanche's virtual machines make it easy to define a blockchain-based decentralized application. So rather than new limited languages like Solidity, developers can write virtual machines in Golang, and using a gRPC API, you can actually write your virtual machine in a language other than Golang, as long as your VM implements a certain interface. So your blockchain can run as a separate process from Avalanche Go and can communicate with Avalanche Go over gRPC. And this is enabled by the RPC chain VM, which is a special VM that uses Go plugin and wraps another VM implementation. The C chain, for example, runs the Coreth virtual machine in this fashion. Coreth is basically our fork of Geth, our fork of the Ethereum virtual machine. And so this is the way it works. The RPC chain VM wraps the C chain and runs it in this fashion. So RPC chain VM has two important parts. There's a client and a server. The server runs its own process and allows the underlying virtual machines methods to be called via gRPC. The client runs as part of the Avalanche Go process and makes gRPC calls to the corresponding server in order to update or query the state of the blockchain. Next, we have subnets or subnetworks, which are dynamic sets of validators working together to achieve consensus on the state of a set of blockchains. Each blockchain is validated by exactly one subnet. A subnet can validate many blockchains, and a node may be a member of many subnets. So to visualize the heterogeneous or rich and diverse nature of the Avalanche network, picture this. A virtual machine is the application level of your blockchain. It's the template and can be instantiated into many different blockchains, some of which are public and some of which are private. A blockchain is an instance of a virtual machine. Each blockchain is validated by exactly one subnet. A subnet can be on a spectrum of public to private and can validate many different blockchains, including many instances of the same virtual machine. A node can be a member of many subnets, validating many blockchains, including many instances of the same virtual machine, some of which are public and some of which are private. So if you were able to, visualize what I just described, you get a sense of Avalanche is truly a heterogeneous network. It's very rich and diverse in nature. And subnets manage their own membership and may require that their constituent validators have certain properties, some of which are very useful. So we'll go over them right now. So regarding subnets, we have compliance. Avalanche's subnet architecture makes regulatory compliance manageable. A subnet may require validators to meet a set of requirements. So for example, you can say all validators in my subnet must be located in a given country or legal jurisdiction. All the validators in my network need to pass these KYC AML requirements. All of the validators in my network need to hold a certain license. These are just examples. These are not prerequisites for running on the existing Avalanche network. I'm just describing some things that you can do with your own subnet, because we believe that regulatory compliance is a big part of the blockchain story going forward. And Avalanche's subnet architecture makes regulatory compliance manageable. We also have support for private blockchains. You can create a subnet where only certain predefined validators may join, and create a private subnet where the contents of the blockchain would be visible only to those validators. So this is ideal for organizations interested in keeping their information private. There's also separation of concerns. In a heterogeneous network of blockchains, some validators would not want to validate certain blockchains because they simply have no interest in those blockchains. The subnet model allows validators to only concern themselves with blockchains that they care about. This reduces the burden on validators. There's also application-specific requirements. Different blockchain-based applications may require validators to have certain properties. Suppose there is an application that requires large amounts of RAM or large amounts of CPU power. A subnet could require that all validators meet certain hardware requirements, so the application doesn't suffer from low performance due to slow validators. And now I want to talk about our primary subnet. So our mainnet launched in August of 2020 with what we call the primary subnet. And it has 3 blockchains live on it today. It has the X chain, the C chain, and the P chain. And so this is a nice visualization that we have showing it. You can see in the middle, we have the 3 chains, the P chain, the X chain, and the C chain. They demo a lot about what's possible in Avalanche. So the X chain, remember, a blockchain is an instance of a virtual machine. So the virtual machine is called the Avalanche virtual machine. It's a DAG, a directed acyclic graph, and it has partial ordering, and it uses UTXOs. So if you're familiar with Bitcoin, or any, Litecoin or Bitcoin Cash, any of the Bitcoin derivative chains, they all have what's known as UTXO, which stands for unspent transaction output. Pardon me. And that's different than what you have in Ethereum, which is an account-based model. So for example, if you're familiar with Bitcoin or what we do on our X chain, we generate a new address for every single transaction. And the reason you do this is because you have this concept of unspent transaction outputs. And the Avalanche network is able to support partial ordering, DAGs, a UTXO. We can also support total ordering, linear blockchains, which is the count model, which I'll explain here in a second. But regarding the X chain, as I mentioned, it's a DAG. It has partial ordering, it's parallelizable, it's prunable, it gets extremely high throughput, 4,500 transactions per second. It has sub-second immutable, irreversible finality, and you can issue your own assets on the X chain. We call them Avalanche native tokens, ANTs, and they can be variable or fixed cap assets, meaning you can, whenever you create your token, you can say that there will only ever be 10,000 Gabriel tokens. We can never issue any more, or you can create a Gabriel token where you can actually issue more tokens. So that's a variable capped asset. There's also this idea of non-fungible tokens. So the X chain has NFTs. They are not compatible with the ERC 721 or ERC 1155 specs from the Ethereum network. They're more like a collectible paradigm, but they do exist. And again, they have high throughput and sub-second finality. And so that's the X chain. It's an instance of the Avalanche virtual machine. You can see on the right, we have the C chain. So the C chain is an instance of the Ethereum virtual machine. It has 100% backwards compatibility with existing Ethereum developer tooling. So if you're used to Hardhat or Remix or Truffle or MetaMask or any of these tools that you would use, Open Zeppelin, any of the tools that you would use in the Ethereum or any other EVM ecosystem developer workflow, you can use those exact same workflows and toolings on the Avalanche C chain. It's one of the reasons it blew up as fast as it did, because developers who were already had a dApp running on Ethereum or Binance, etc., only needed to add a new network ID and they could deploy their smart contract to our C chain, and it just worked right out of the box. So as I mentioned, it has 100% backwards compatibility. So, you know, you can do ERC20s, ERC 1155, ERC 721 for non-fungible tokens. You can create distributed autonomous organizations and prediction markets, and so much more. The Avalanche C chain is a linear blockchain, so it has total ordering, unlike the X chain, which I mentioned was a directed acyclic graph with partial ordering. So the C chain is very, very good for smart contracts because it has a total ordering of all of the state transition functions. So you can do smart contracts, and it uses the account-based model. So if you remember, I mentioned that the X chain uses UTXOs and is a DAG. The C chain is a linear chain, and it uses the account-based model. On the left, you can see that we have the P chain. So this is our platform chain. This is like our administration chain. We use this to launch new blockchains, to create subnets, to add your node as a validator, to add your node, to delegate your stake to an existing validator. And the P chain is very interesting because it is it has total ordering, but it uses the UTXO model. So it's kind of like a mixture of the X chain and the C chain. Instead of it being a DAG, it has total ordering like the C chain, but it uses UTXOs instead of the account-based model. And then you can see that in the middle, there is a red line that's drawn between the three circles. And that represents that you're able to do cross virtual machine or cross blockchain asset transfers. Pardon me. So today you can launch an asset on the X chain. You can then swap it over to the C chain. You can then swap it over to the P chain. So AVAX is a fixed cap asset. There will only ever be 720 million AVAX issued, and it was actually issued, or minted, I should say, and it was actually issued on the X chain. So the AVAX is an Avalanche native token, but we're able to swap it back and forth between the virtual machines, and you can see that with that red line. And so what's interesting is today you can swap assets back and forth between virtual machines. You need to use a bridge if you want to bridge assets between different subnets. But in the future, we'll have built-in native to the protocol, the Avalanche protocol, the ability to swap assets natively between not only virtual machines, but between the different subnets as well. And so one of the huge paradigms that we're witnessing is what I'm calling the bridging, which basically all of these networks which spin up that have value are then having bridges between them. And bridges are one of the most interesting things that are happening in the, the blockchain paradigm right now. And we will actually go a step beyond bridges, where we will have native asset transfers between different blockchains. So this is what's known as the primary subnet. And as I mentioned, there is the X chain, the P chain, and the C chain. This has been live on the Avalanche network since August 2020. So now let's go over AvalancheJS. So what is AvalancheJS? AvalancheJS is a JavaScript library for interfacing with the Avalanche platform. It's built using TypeScript and is very modern and idiomatic. And I'm a huge advocate of TypeScript. If you're working with web tech and you're not using TypeScript, then you really should take, the afternoon or however long it takes you to on-ramp into a TypeScript workflow. It's not a huge overhead. The overhead required isn't huge, and the payoff is absolutely massive. So TypeScript lets you think about your abstractions more clearly. It will cause your developer tooling to come alive with suggestions and catching errors. You can detect errors at compile time instead of at runtime. And every single time that I have converted a .js file to a .ts file, I have seen bugs scurrying for the darkness. So especially in the context of value-bearing assets, which is what crypto is, you absolutely need to be using TypeScript. So again, I just want to be a huge advocate of taking the afternoon and on-ramping into a TypeScript workflow if you're using JavaScript, which most likely everybody is because it's the language of the web, and the web is ubiquitous. AvalancheJS is intended to support both browsers and Node.js. It supports the client and the servers. So, you can use it in a React app, you can use it in an Angular web app, you can use it in a Node.js command line utility. The AvalancheJS library allows one to issue commands to the Avalanche full node APIs. And there are 3 areas of functionality. We have a Json Rpc, we have a keychain, and then we have transaction serialization. And the Json Rpc is the first area of functionality, and it's a remote procedure call. The first area of functionality is the Json Rpc, which is a remote procedure call protocol encoded in JSON. And it's very similar to XML RPC protocol, defining only a few data types and commands. Json Rpc allows for notifications, data sent to the server that does not require a response, and for multiple calls to be sent to the server, which may be answered asynchronously. And as I mentioned, Avalanche is a network of over 1,500 full block and vertex producing nodes. And each of these nodes may optionally enable API endpoints which developers can interface with over Json Rpc via AvalancheJS. And the Json RPCs are as follows. We have the Admin API, which can be used for measuring your node's health and for debugging. Note that the Admin API is disabled by default for security reasons. So to run a node with the Admin API enabled, you need to pass in the config flag --API-admin-enabled equals true. And of course, all of this is available on our documentation. We have the auth API. When you run a node, you can require that all API calls have an authorization token attached. And this API manages the creation and revocation of authorization tokens. An authorization token provides access to one or more API endpoints. And this is useful for delegating access to a node's APIs. The tokens expire after 12 hours. So you'll have to have an awareness of that and recreate them after 12 hours. Or if you need them for less than 12 hours, you can revocate them. We also have the Avm API. This is for the X-Chain. So the X-Chain is Avalanche's native platform for creating and trading assets. And it's an instance of the Avalanche virtual machine, as I mentioned. And this API allows clients to create and trade assets on the X-Chain and other instances of the AVM. We also have the Evm API. This is the API for interfacing with the C-Chain, which, as I mentioned, is our instance of the Evm, the Ethereum virtual machine, and has 100% backwards compatibility with existing Ethereum Evm developer tooling and workflows. We have the Health API. This API can be used for measuring a node's health. The node runs a set of health checks every 30 seconds, including a health check for each chain. And this method returns the last set of health check results. So it's very useful for measuring a node's health. We have the Index API. Avalanche Go can be configured to run with an indexer. That is, it saves or indexes every container, whether it's a block, a vertex, or a transaction, that it accepts on the X-Chain, the P-Chain, and the C-Chain. To run Avalanche Go with indexing enabled, you have to set the command line flag --index-enabled to true. We have the Info API. This API can be used to access basic information about the node, such as blockchain ID, network ID, node ID, etc. We have a Keystore API. Every node has a built-in key store. Clients create users on this key store, which act as identities to be used when interacting with blockchains. A key store exists at the node level. So if you create a user on a node, it exists only on that node. However, users can be imported and exported to between different nodes using this API. We have a metrics API. The API allows clients to get statistics about a node's health and performance. And then we also have the P-chain API. So this API allows clients to interact with the P-chain, which maintains Avalanche's validator set and handles blockchain creation, subnet creation, as I mentioned, adding validators, adding delegators, etc. Next, we have transaction serializations. So that was Json Rpcs, but each node also has a set of endpoints which can optionally be enabled to query over HTTP using something like Postman or via AvalancheJS. So now let's talk about transaction serializations. Remember that I told you that technically speaking, a virtual machine is a state machine, and it specifies the blockchain state transition function, transactions, and the API through which users can interact with the blockchain. So every blockchain on Avalanche is an instance of a virtual machine, and firing off a transaction triggers a state transition in your state machine. And every virtual machine on Avalanche will have a set of transactions, serializations. So the Avalanche virtual machine has the base transaction. This is for moving, sending AVAX back and forth between addresses, for sending variable and fixed cap assets, for sending non-fungible tokens. It has create asset transaction. This is for creating new variable or fixed cap assets and for creating non-fungible tokens. It has an operation transaction. This is for minting variable capped assets and for moving, for transferring NFTs. It has an import transaction and an export transaction. As I mentioned, native to the Avalanche protocol is the ability to move assets back and forth between the different virtual machines, and that is done by these export and import transactions. So each one of the virtual machines that implements this interface is then able to move assets back and forth between them. So I can actually export some AVAX from the Avalanche virtual machine, and then that AVAX goes and sits in an unspent transaction output set, an atomic, we call it the atomic outputs. And then from, let's say, the C chain, you can call the import transaction. And then you can say, give me any atomic outputs that are coming to my address from the X chain, for example, and it will give you all of the ones that you just exported from the X chain. So that's kind of how swapping assets between the virtual machines work. As I mentioned, in the future, we'll be able to do something similar between the subnets. Currently, if you want to transfer assets between the subnets, you need to use bridges. There's also the Ethereum virtual machine, which, as I mentioned, has 100% backwards compatibility with existing Ethereum APIs. We also have the import and the export transaction. So you're actually able to swap assets from the EVM, from our C chain, back and forth between the X chain or the P chain. And we have the platform virtual machine. So this has create subnet transactions. So as you might imagine, this allows you to spin up your own subnet. When you create a subnet, you pass in a set of control keys and a threshold. So for example, you pass in 3 keys and a threshold of 2. And that is saying, if anybody wants to make any changes to this subnet, if they want to add a virtual machine, if they want to add validators, we need at least 2 out of these 3 addresses to sign a threshold control signature. So that's the way that works. We have the add validator transaction, which allows you to add a node as a validator on the primary subnet. One of the prerequisites for spinning up your own subnet and having validators is that your validator must also validate the primary subnet. So every subnet's validators is actually a subset of the full validator set, which exists on the primary subnet. We have the add subnet validator transaction, which allows you to add validators to subnets. We have the add delegator transaction. So currently it takes 2,000 AVAX in order to be a full validator of the primary subnet. That's a relatively high amount. That value will be changing in the future, but today it's hard coded to 2,000. But you can still delegate if you have at least 25 AVAX. You can delegate your tokens to an existing validator, and they can charge you a fee, and that will increase their weight, which increases their statistic chance of being queried when creating a new block or a vertex. And then, as I mentioned, you still get some of the reward that comes from validating minus the fee that they charge you. We have the create chain transaction, which allows you to spin up your own chain on a subnet. As I mentioned, a chain is an instance of a virtual machine. So once you create a subnet, once you add subnet validators, then you can add blockchains to it, and you have your own subnet running. And of course, we have the import and the export transaction, which, as I mentioned, are useful for moving assets between the X chain, the P chain, and the C chain. And then lastly, we have a keychain. So as I mentioned earlier, with Avalanche Go, a full node has a key store, which enables you to create users with key pairs and sign transactions via a full node's key store. The problem is this requires you to store your keys on the full node, which is a target for malicious hackers, and we consider this an anti-pattern. That is why Avalanche JS can act as a keychain in addition to having transaction serializations for the different virtual machines. And you can create transactions to trigger virtual machine state transitions and sign them locally without your keys ever leaving your machine. You can even leverage tools like a Ledger hardware wallet for even greater security. The Avalanche JS keychain supports the SecP 256K1 curve on ECDSA key pairs, which is in line with the 3 virtual machines of the primary subnet. Okay, so in summary, Avalanche is a global financial network for the issuing and trading of all digital goods. We enable potentially millions of validators to process thousands of transactions per second with near instant finality using a protocol which is completely green and quiescent. And we've paired this high throughput and fast finality protocol with an architecture that can meet the needs of unique financial services and decentralized applications. We accomplish this through the notion of subnets. So subnets allow anyone anywhere to spin up a tailor-made network with custom virtual machines and complex validator rule sets. And Avalanche is a network of networks. It's a platform of platforms where we envision thousands and thousands of public and private subnets all emerging into this global marketplace, which we call the Internet of Finance. So I just want to express gratitude to the team for having me today. I want to express gratitude to anybody who listened or listens in the future. And of course, I want to express gratitude to the team at Ava Labs. It's truly an honor and a pleasure to work with all you amazing block stars to change the world each and every day. I really do believe that our work is going to have an impact similar to the people who created the internet in the 60s and the TCP/IP stack in the 70s and the web, of course, in the 90s. Our work is going to be transformative for generations to come. So, as I mentioned, my name is Gabriel Cardona. I'm developer evangelist at Ava Labs. You can find me at CG Cardona on Twitter and Telegram. Please feel free to reach out to me. Enjoy the rest of your time at this hackathon, and best of luck to all of the amazing builders. Okay, so that is it. So now I think we wanted to jump on over. Do we have time for Q&A, or do we need to jump on over to Aaron?
No, feel free to answer the questions.
Okay, so let's see what we got here. It says, is Avalanche a layer 2 solution of Ethereum blockchain? No, we don't think of ourselves that way. We think of ourselves almost like a layer 0 or a layer 1. We enable people to spin up their own blockchains, and we have a library called the Subnet Evm, which is an instance of the Ethereum virtual machine that is, primed for use on Avalanche's subnets. So anybody can launch their own instance of the Ethereum virtual machine, but it's not like a layer 2 solution that sits on top of Avalanche. It is a layer 1 blockchain, and then you can use bridges to bridge assets between existing blockchains. So you can bridge over into other Avalanche networks, or you can even bridge into Ethereum or Bitcoin. So we see ourselves as a layer 0 or a layer 1, but we're not a layer 2. It says, what is the cost to deploy a subnet onto Fuji? The cost, I don't know the cost off the top of my head, but it is very inexpensive. The most expensive part of launching your own subnet is having 2,000 AVAX to stake and be a validator. And we suggest that you have a minimum of 5 validators. So, we're talking 10,000 AVAX staked. That's a non-trivial amount of money. The actual cost of spinning up the subnet is relatively small. It's just the cost of a transaction. And on Avalanche, our transactions are very, very inexpensive. Plus, you would need to factor in the cost of running your hardware, either on the cloud or if you have your own dedicated hardware in a co-location or something like that. But I would say the most expensive, if you will, part of running your own subnet is staking. And that's not spending them. So in theory, of course, you would be able to get them back. And you're going to be getting, I think right now it's less than 10% or something like that per year that you would be getting in rewards from staking. So ultimately, you can think of it kind of like an investment, if you will. But the most expensive part is simply having the AVAX to stake. It says, I'm completely new to the Web3 environment, but have created a handful of stacks. Are there resources and sample apps with TypeScript or JavaScript? There are. So if you go to Avalanche JS's GitHub repo, there is an examples directory where I have dozens and dozens. There's over 60, maybe even up to 100 example scripts. So there's tons of example scripts there. Also, there are, if you use something like Truffle, there are Truffle boxes, which are basically all the scaffolding of like a React app or an Angular app or something like that. You can go and use Open Zeppelin smart contracts. So basically there's even an Open Zeppelin wizard. It's a little web GUI where you can say, I want to create a non-fungible token and I want it to be, mintable and burnable. And you can click a couple boxes and it'll actually output the smart contract for you. So I would say between using AvalancheJS's example scripts, using Open Zeppelin's contracts and their web wizard, and then using something like Truffle boxes, most of the work is really done for you. You just need to wire it all together and then, sprinkle in your special sauce, which is whatever your dApp is that you're building. Let's see here. It says, you mentioned the Ava Labs career features after checking through the docs. Hold on. It says, after checking through the docs, it seems jobs are offered to only Rust developers in the engineering department. I'm not sure what you looked at, but that doesn't seem accurate to me. Yes, we are. So, because Rust isn't one of our primary languages. Our primary tech stack at Ava Labs is Golang, TypeScript, and Solidity. And yes, we are absolutely hiring JavaScript or TypeScript developers. We definitely are building out our front end team, and then we have several different projects that leverage web tech. So yes, absolutely. Check out avalabs.org/careers, and you will see we're not only hiring for Rust, most definitely not. And even if really what we're hiring is amazing people, we're willing to teach you the languages, right? So if you don't know Golang and you happen to only know Rust, that's okay. We're confident that you can relearn Golang on the job. Really what we hire is we want amazing people who, are creative and easy to get along with and hardworking and are wanting to have a huge impact on the world with their work. And so that's what we're looking for. And then it says, you suggested picking up TypeScript. My question, can a newbie pick up TypeScript without prior knowledge of JavaScript, or should be after? I think you could pick up TypeScript without knowledge of JavaScript. They're very, very similar. They're like, 90% the same language. It's just TypeScript has a little bit of extra stuff, interfaces and native classes and optional types, that kind of stuff. So yeah, I would say if you don't know either and you're just learning, start with learning TypeScript. You'll be learning JavaScript along the way, and there's no barrier to entry there that says I have to know JavaScript before I can on-ramp into TypeScript. So I just encourage you to start with TypeScript out of the box. Okay, that seems like all of the questions.
Yep, that's pretty much it. Thank you, Gabriel, for such insightful presentation. And that's it. Thank you so much for your time.
Yeah, thank you so much. Cheers. Good luck, Aaron.
Yep, thank you. So next time, we actually have Aaron, who will be covering Scaling Web3 with Subnets. So Aaron, the time is yours now.
Awesome. Hey, everybody. How's it going? Give me 1 second. I'm going to share my screen for the Scaling Web3 with Subnets. Thanks, Gabriel, for a great talk. I really enjoyed listening to that for the past 20 minutes. I think I joined a little bit late. Just to give you guys a heads up, there's going to be a little bit of an overlap in content between the content I'm going through and Gabriel's, but I think it's going to be a different angle. So hopefully you guys can get a lot out of it. Let me see if I can share my screen here. Great. Are you guys seeing what I'm seeing? Scale with Subnets?
Yep, all good.
Awesome. I'll kick it off then. Hey, everybody. My name is Aaron Buchwald. I'm a software engineer at Ava Labs. I work primarily on the platform squad. So that's the team that is building Avalanche Go, the core consensus client. And I work primarily on our virtual machine implementation. So that's Core ETH, the virtual machine powering the C chain. And I also work a lot on Subnet EVM, the fork of Core ETH that we use to power different subnet different customized versions of the EVM for people to launch their own subnets. So this talk is going to be about how we've achieved scale by running on subnets, and a little bit also about the background of some other approaches in the industry and how subnets are an example, as Gabriel mentioned, of heterogeneous blockchain networks. So first of all, this is part of where the overlap comes from, but I want to break down what a blockchain is for all of you guys to start from the very most basic aspect of it. So first, a blockchain is essentially a state machine in its most simplest form. There's some initial state of the world that's included in the Genesis block, and it basically says that this is the original state of the world. So in the Bitcoin network, that might say Satoshi Nakamoto has 100 Bitcoin, and it might say some other accounts have some amount of funds, or it might say something more complicated or different, such as this blob of data is stored at this address. It's completely up to the virtual machine in terms of what the semantics should be. Next, there's some definition of what a valid state transition going from state A to state B. And basically each block is a state transition that takes the global state of the network from one block to the next. So by the time we're at block 1000, the state of the world at that point is really just the summation of all of the block's state transitions up to that point. Next, there's a validator set. And this is the network of nodes that are actually performing consensus to validate the chain. Each node is attributed some weight, and this is usually based off of what Sybil control mechanism is being used. So the Sybil control mechanism is typically either proof of work, proof of authority, or proof of stake, and it decides what percentage of the network's weight should be attributed to each individual node. So if it's proof of work, your share of hash power on the network essentially gives you that portion of control of the network. If it's proof of stake, if you've staked 100 AVAX and there is a total of 1,000 AVAX staked on the network, you would essentially be voting for 10% of the network, and you would have a 10% share. Last, there's the consensus protocol aspect, and this is the part where we need to figure out how to decide what the next block is in consensus. So this is where the network decides not what the state transition is, but what the next state transition is to add. Important characteristics to be aware of here as developers and also of both applications as well as the blockchain itself are finality. Finality is this notion that when does my transaction or the thing that I want to do go from a state where it may or may not get reverted, it may or may not get included in the chain, to a state where it is absolutely included, it has happened, and there is no chance of it being reverted. Next, we have two properties that are really borrowed from distributed systems: safety and liveness. So the idea of safety in the most general academic sense is nothing bad will ever happen. And in the context of distributed systems and consensus protocols, this really means that no two nodes that are virtuous, that are behaving correctly, are ever going to agree on two different things. So this is to say, if there are two blocks, block A and block B, both at height 1000, then two correct nodes will always agree on which one of those blocks should be accepted at that point. Next, we have liveness, and liveness is the notion that the network is always going to be making progress. There's never going to be a point where it's not able to continue to make forward progress to accept the next block. So now we'll break down a little bit of the different consensus families. I'm going to kind of breeze through this because I believe Yuho, one of my colleagues, gave a talk on consensus earlier this week. So if you want a real deep dive into Avalanche consensus and consensus in general, you should check out his talk. The first family is really classical consensus protocols. And these protocols rely on the idea of, if I am one node in the network and there are 10 different nodes, I'm going to ask every single one of them and send every single one of them a message to see what they think. And so there's a voting protocol that relies on all-to-all communication. And this means that there is quadratic message complexity based off of the number of validators in the network. This actually has very, very quick finality, but the problem is that it doesn't scale to a much larger number of participants. So this works well for small operating systems if there are 5 to 10 components, but this doesn't scale to large distributed systems with the blockchains that we use today to have thousands or hundreds of thousands of different nodes in the network, because the complexity increases with the number of different nodes that are running the consensus protocol. Next, we have Nakamoto Consensus, or heaviest chain consensus. This is a very robust protocol. It has no need for a precise membership, but it has much longer degree of finality. The way that this works is essentially every block has some proof of work included in it, and the definition of what is accepted or what is preferred by every node in the network is just whatever has the most work done on top of it. So as long as every node in the network prefers that, then when mining is done, work is done, it allows them to append new blocks to the network, but you don't really have a notion of finality until you've done an irreversible amount of work on top of a certain block. Otherwise, if somebody came along with more hash power, they could potentially mine a new block off of some fork and reorg some other blocks out of existence, which can lead to very slow finality. And it makes it hard to build applications on top of this if you have to worry about that. Take, for example, if you're trying to use cryptocurrency as a currency to buy a coffee at the store, if you have to wait for some amount of time before that transaction is actually finalized, then you kind of have to wait in the coffee store for 30 minutes before you can walk out and actually pay for it. And this typically leads to different notions of when is it acceptable to consider a transaction final? Is it included in the mempool? Is it included in a block? Is there some number of blocks deep that it's been included? And that is a little bit more of a shaky basis to build on top of for applications. And next, we have this third family of consensus protocols, Snow Consensus. And there's a decent number of different protocols today that are claiming to be the next great family of consensus protocols. So I'm not going to say that this is the only third family of consensus protocols, but Snow Consensus is based on the idea of a repeated subsampling algorithm. And that looks a little bit like this, where instead of having every single node in the network communicate with every single other node, what you do instead is sample a small portion of the network. So you can see in this graph, there's one red square that's sampling all of the purple or pink squares. And it's only going to sample some small portion of the network, and it doesn't have to scale that up to an increasing number of nodes in the network. And by repeating this process over and over again, you can actually accrue confidence that if on the first sample and the second sample and the third sample and so on, if all of them are saying the same thing, all of them agree that one thing is correct, then over time you can actually accrue sufficient confidence to come out with a probabilistic finality. So what this really looks like is, as all of the nodes in the network are running the same protocol at the same time, you can come to a degree of finality where you know that the entire network is going to reach consensus on this after a relatively short number of rounds. And that's how Avalanche and the Snow family of consensus protocols reaches finality very quickly. So you can see in this graph, there's the network in the first image is somewhat split, and it starts to converge somewhat randomly towards blue. And this is, as it's getting darker and darker, you can see its confidence in that color is increasing. So the next part of this, to go into more detail, is Avalanche Subnets. So an Avalanche Subnet is really the conjunction of these three things that we talked about. There's a virtual machine, which is essentially the state machine for your application for the blockchain. It defines the state of the application and the logic behind it. It provides some degree of access control, who has access to that state, who has the ability to modify different pieces of that state. And it typically provides APIs to interact with that application as well. Next, there is a validator set, which is defined for an entire subnet. And this is always a subset of the primary network validators. So what that means is, in order to be a validator of an Avalanche subnet, you have to also be a validator of the primary network. This is also based on proof of stake. It could be either permissioned or permissionless. That means that for a permissioned subnet, there's essentially someone who owns the subnet and can add different validators at an arbitrary weight, whereas permissionless is something that we're still working on and is going to be coming out very soon. And permissionless will allow people to stake their own token on their subnet in order to use the same proof of stake protocol as an Avalanche. Now, one of the nice things about Avalanche subnets is that it takes care of all of the networking and consensus for you. So all that you have to do as a VM implementer or a user is to supply the VM that you want to use, and then Avalanche Go, the consensus client, will actually supply the consensus engine that drives consensus and decisions for that network, and using this repeated subsampling algorithm. And it does this with 1 to 2 second finality and parameterizable safety and liveness. So the next phase of this is, how do we actually go about orchestrating subnets? So how do you create your own? The way to do this all happens on the platform chain. So to understand this, the platform chain is one of the virtual machines or blockchains that exists on the primary network. The primary network, as Gabriel mentioned, has the X chain, P chain, and C chain. And the P chain is really the central component of all of this. The P chain is the part that orchestrates who is a validator on the primary network, what is their weight. This is where all of the transactions take place in order to add validators, add delegators, as well as where we take care of the creation of new subnets and the orchestration of what the validator set should be for those subnets. And so the P chain is where all of these subnets actually exist. Their genesis information, the creation of them, and the maintenance of what the validator set is for that subnet, in addition to what blockchains exist on that subnet. The P chain actually orchestrates within Avalanche Go, starting and creating new virtual machines, new consensus engines for each of the blockchains created on different subnets. And the P chain can actually create multiple different subnets, each with a unique individual validator sets. And each subnet can have its own custom set of blockchains. So the way that this shakes out is that the primary network has the XP and C chain, and additional subnets have their own different set of blockchains. They're not constrained to run the exact same one. They can actually use a custom virtual machine. Anything that implements the virtual machine interface supplied by Avalanche Go, as the C chain, P chain, and X chain do, then they can actually run that exact same application logic. So this gives developers the ability to create their own virtual machine that's custom tailored to their own application. The great thing about this is that subnets take the approach of horizontal scaling. So a lot of other applications, a lot of other blockchains are taking the approach of sort of vertical scaling based off of L2s. And many other blockchains are taking the approach of having very minimal gas fees. One of the things that happens is every blockchain, no matter what the consensus protocol is, has some limited capacity. There's never going to be any protocol that has unlimited capacity. There might be one that has higher capacity than there is actually demand for, and that's sort of the goal. But in the intermediate term, there's going to be some limited capacity, and no matter what you do, whatever your blockchain is, it's going to be trying to take up that capacity. And if it takes up more of it, then the consensus protocol can't scale to meet that. So what typically happens is that blockchains need to increase their fees, or they need to just keep artificially low fees and have sort of a degradation in performance when the demand exceeds the capacity. If the demand exceeds capacity and fees don't adapt to sort of reduce demand at that point, then some of those transactions just won't be able to get into the consensus protocol, and there will be a big slowdown. The approach that we take, similar to Ethereum, is that we have dynamic gas fees. And there's a bit of a gas market for it. So in order to be included in a block, you have to pay a fee. And if the amount of demand on the network or the amount of utilization that's taking place exceeds the target capacity for the C chain specifically at that point, then the gas fees will increase. So what you see on this graph is the gas fees sort of increasing as there's higher and higher demand at different points in the history of the Avalanche network. Now, one of the most popular applications on the Avalanche network and one of the most gas hungry ones was Kribata. So Kribata was using a huge amount of gas. It took up, I think, almost 80% of the gas on the Avalanche network for a long period of time. And because it was a game, there wasn't necessarily a huge need for their application to actually be running on the Avalanche C chain. There wasn't really a need for composability. It wasn't a game that was going to require immediately transferring those assets or composability between, for example, an automated market maker and a lending protocol in order to facilitate arbitrage opportunities. It really could exist in its own isolated network. And the fact that it existed instead on the C chain on top of everything else meant that that limited capacity the C chain had, it was taking up a very large portion of that and driving up fees for every other project. What happens, what you see here in early May, is that as soon as Kribata switched to running on its own subnet, you can see that the gas fees drastically reduced on the Avalanche C chain. And that's because they were running on their own subnet at that point, and the amount of demand on the Avalanche C chain went down drastically. So the nice approach that horizontal scaling takes is that you can sort of think of each individual subnet as a multi-lane highway, where there's, on the primary network, there are 3 lanes for the X chain, P chain, and C chain. And the highway is essentially going from point A to point B, where point A is, sort of the entry point to the highway. You're issuing a transaction to the network and saying, hey, please finalize this. And so point B is simply the finalization point. It's the point of no return. There's finality. This has been included in the chain, and we can build applications on top of the notion that this has happened. And so since we only have the XP and C chains, each of them has a limited capacity. And throughout most of the history of the network, the C chain was the one that had the most demand. And so you can see here, there's essentially a lot of traffic on the network and it causes congestion. The nice thing about the approach of horizontal scaling is what you can essentially do is build parallel highways where each one can run completely independently. Each one is running the same consensus engine, so you can achieve the exact same speed. But there's no need to actually run those applications on the C chain. They can run on their own separate subnet and achieve that same speed on their own highway. So that's what Krabata has done in launching on their own subnet. And the one limiting factor to this is really the number of validators that you may have. So because Avalanche Subnets, each validator is required to be also a validator on the primary network, this becomes sort of the one future bottleneck. Because we have to, if there are, let's say, 10,000 subnets, and each of them wants the maximum level of decentralization, the maximum level of decentralization in the context of Avalanche would be that every single primary subnet validator is validating every single subnet. And that sort of takes away from the purpose of horizontal scaling, where you have this notion only some subset of the validators are going to validate the Krabata network. And that means that, okay, those validators can run with much higher requirements. They can run with higher storage, higher CPU requirements. But in order to validate the Avalanche primary network, it's not necessary to take on that extra overhead. So the interesting thing that we're going to see in sort of this potential Cambrian explosion of new subnets is, how does demand for those validators shift? How are those validators going to scale up? And that's something that, based off of the fact that each Avalanche chain is running its own independent instance of consensus, if there is sufficient demand for more subnets and there is sufficient demand for high capacity subnets, because Avalanche is running each of those consensus instances essentially independently, it should be fairly easy, and this is not something that we've implemented yet, but it's certainly possible to sort of implement it where those nodes can actually scale to take on, to run consensus independently on each of those chains without adding too much additional overhead. You can sort of scale up at that validator level as each of those individual nodes to make them more performant, where if they want to pay extra or use much more powerful hardware to run multiple different subnets, if those are all financially worthwhile because those subnets have their own rewards, then they can. And it's actually built in a way where it should be fairly straightforward to scale them out in that way. So the question then is really like, what can be built on a subnet? And the answer is pretty much anything. Since a subnet has the ability to run any virtual machine, you can run basically any application that can rely on state machine logic. So the question for you guys as hackers at this hackathon is really, what application does it make sense to move to a decentralized context? Because you can build, you're not limited to running on top of the Evm, you're not limited to running on top of any other existing smart contract or language. You can really build anything that you want at the VM level. So for very application specific use cases, you can actually just bake the state machine logic of your application directly into the VM and rely on Avalanche to transform that into a decentralized network. And you can sort of change and tune the parameters to say whether or not all of that data should be public, whether it should be private to your subnet validators, and exactly what that should do. And the very nice thing about this is, anytime that you're building on top of some existing interpreter or some existing machine, there's some level of abstraction and some level of overhead that goes along with it. So for example, any application that you build on top of the EVM interpreter, and so I work a lot on the EVM, it's my primary focus. Any application that you build on top of it is running on top of EVM bytecode, running on top of the EVM interpreter, that's running on some machine level language. So if you're running on the C chain, you're running on top of the EVM interpreter, running on Core ETH, on Avalanche Go, and there's a couple of different layers of abstraction. And that program would naturally be much faster if it was actually just implemented in the native language that was implementing the EVM interpreter. Otherwise, there's always going to be an additional level of abstraction, the overhead that comes with it. And so for application-specific blockchains, this is a huge area of potential optimization. If you have a very focused application and no need to rely on the EVM, then you can actually build your own application directly at the VM level in, let's say, Golang within Avalanche as a as its own VM and connect it to Avalanche Go. And you can build that so it's going to be significantly more performant because it's going to be tuned directly to your application. You don't have to operate on all of these different levels of overhead. Now, that's a little bit scary and that's a little bit hard to do at the moment. And so one sort of intermediate step is my pitch to you guys as to what a good potential project would be and what potentially interesting new approaches there are within this space is, this is sort of the subnet roadmap. We have customized EVM. So one of these is we already have a subnet EVM implementation. And so if you guys are familiar with the EVM and interested in it, one of the notions based off of a lot of what I just said is we've developed this notion of stateful precompiles. And the idea with the stateful precompile is that there's a sort of middle ground between wanting to develop your own custom VM tailored 100% to your own logic and wanting to actually deal with all of that. And so the idea of a stateful precompile is that it allows you to build custom logic specific to your VM that will only run there within Golang, so directly within the subnet EVM implementation, and it will be directly callable from the EVM. So you can implement your program, your application-specific use case directly in Golang, so it'll be more efficient than building something in a smart contract on top of the EVM interpreter. But you can then call it directly from Solidity. So you don't have to build all of the tools to interact with your application. You can actually just build a stateful precompile, and then you would then interact with it in the exact same way as if it were a smart contract. And this is a really powerful notion because there's a huge suite of tooling in JavaScript, Rust, Golang that already exists for interacting with things that are built for the EVM. So this is a way to avoid building something separate from the EVM. This is a way to build something completely custom, but still allow you to use that entire existing EVM ecosystem of tools. Next, we have, application-specific blockchains. This is sort of the next step from customized EVM. If you want it to be even more application-specific, this comes with a much larger overhead because you have to implement all of the VM invariants, but it does allow you to optimize 100% for your application. And this allows you to sort of implement it however you want. You're not necessarily constrained to the EVM tooling. The EVM tooling is great if you want to have sort of a low lift, but if you want to completely rebuild an application and build something completely new, then you might want to build an entirely custom VM so you can implement it exactly how you want. You don't have to support all of the existing Ethereum APIs, and you can actually optimize a ton of different things by not relying on all of that as well. So this is a huge area of potential growth that is happening in the future. This is definitely something that a lot of people are putting a huge amount of work into. One example of this is, and this is not within the Avalanche ecosystem yet, but there's all of these projects that are building on top of the Move VM that was implemented at Diem. So this is a new runtime, a new programming language and paradigm to build decentralized programs on top of. They have taken the approach of not calling it smart contracts, but something like this is really not an application-specific blockchain, but it's building its own completely different state machine for people to build on top of. And so that's a sort of area where we see a lot of growth potentially on Avalanche, is any one of those state machines that people build, we can very easily launch them as subnets, as their own VMs, so people can access them and unite them with the consensus protocol from Avalanche. Next, we have this sort of approach of new SDKs and VMs. So the process of making it easier to build virtual machines. There's already a group of off-the-shelf VMs from Subnet EVM to Spaces VM and Blob VM, but we don't necessarily have a ton of the SDKs for building new virtual machines. That's one thing that if somebody wanted to build something like that, an SDK to make it easier to build a VM and then some small virtual machine on top of that SDK, would be a very, very interesting hackathon project. And the idea here would be really to make it so you have a whole suite of tools to plug and play the Avalanche ecosystem. And there's sort of two pieces of the puzzle for this right now in the way that I see it. We have, if people want to build a VM that's completely from scratch for some custom application, then we want to be able to support that easily. We want to give them the SDKs to completely build their application just within the context of the VM. Separately, there's lots of other virtual machines or state machines that have been implemented out there, other blockchains that exist, from zero-knowledge proof-based VMs to Move VM, and those already have their existing blockchain implementations. So this is sort of the other piece of it, which is for all of those that already exist within a very similar context, it would be great to build the tooling that's necessary to very, very easily migrate those to an Avalanche VM. So right now we've done this for Core Ethan Subnet EVM. So these are really the only forks or other projects that we've built. These are both derived from Go Ethereum. So a huge thank you and shout out to that team for all of their fantastic work. And we've adopted that. The work that we've done is really adopting it to the Avalanche VM specification and making that fit into our consensus protocol. So building out the tooling to do that very easily for some arbitrary VM would be an absolutely huge improvement to the Avalanche ecosystem. So if you're interested in a hackathon project there, that's a really, really interesting place if you want to either build the tooling to make that an easy process, or if there's some other blockchain that you're interested in and think could belong in the Avalanche ecosystem, belong within the Avalanche ecosystem, that would be a very, very interesting thing to fork and sort of build into an Avalanche VM. Lastly, I have this sort of image of what I think a really, really cool stateful precompile could be. The idea of this is to provide stateless storage today. So stateless storage is a big topic on the Ethereum roadmap. The idea is that, or actually not stateless, stateless storage, but the idea is that they want to create a stateless client, or the ability to run an Ethereum node implementation where instead of storing the entire active state of the network, we talked about the state machine, the entire state of every contract and every account as of some point, what would be really cool to have the ability to do instead is to just store the Merkle root hash of all of that data. So one of the cool things about Ethereum is that it uses a Merkle tree or Merkle tree to store all of the data so that you have a provable record of what the key value pairs are in it. And the thing that would be cool to build on top of this in the context of a stateful precompile is, even though that's a little bit longer off, one thing that we could do is build a stateful precompile to provide similar functionality directly to contracts themselves. Storage is, for that very reason that it's sort of a bottleneck in the Evm and Ethereum ecosystem, the most expensive operation within the Evm. And one thing that would be particularly interesting is to take that same approach of providing a stateless client through a Merkle tree directly through a stateful precompile to existing contracts. So that instead of doing this at the client level first, what we could actually do is implement something to provide stateless storage and the exact same functionality to a smart contract itself, so that it could then, instead of storing its data directly within the EVM, it could store only a Merkle tree root and then update, delete, and commit versions of that via a smart contract accessing that precompile. So that would be a very, very cool, very interesting application for a hackathon project, honestly. That would be one that I'd be very, very excited to see. And so far, I haven't been able to convince anyone to take that on at a hackathon, but I think it's really the perfect fit. So if you have any questions about that, I'd love to chat with you guys about it. But yeah, that's pretty much it for my presentation. Thank you guys so much. Really enjoyed chatting with you guys today and excited to answer you guys' questions. I see there are a couple. Let's see. Justin, should I just open up the Q&A and start answering questions?
Yeah, please go ahead.
Great. So 100% agree that better tooling would be an amazing project, but would that qualify for the DeFi and game tracks? I don't know what the different tracks are for this hackathon, to be completely honest. So I unfortunately can't answer that. But one thing that you could potentially do if you were to build out the tooling for this is that you would probably want to actually demonstrate that that tooling works. And so my approach to that, if I were at a hackathon, I love hackathons, by the way. But my approach to that would probably be to build out an SDK that's hopefully as easy to use, as generic and usable for other projects as possible, and then to build some application on top of it. So one thing that could be really interesting for this sort of hackathon and is a big area of innovation right now is there's a large number of different automated market makers. There are a large number of different decentralized exchanges that operate at the EVM level, and lots of them are built at, on top of different virtual machines as well. One thing that would be very interesting is to build that directly into a subnet. So if that's something that you'd be interested in, I could very easily imagine how you could, as one part of a hackathon project, build out a generic SDK And then as a separate part, you guys should be building out teams either way. So as a separate part, you could actually use that SDK. So you could sort of split up your team and say, all right, here's the interface we want to build. And then, all right, here's the application we want to build on top of that and build it directly in that way. So you could do that with either a DeFi application as a sort of proof of concept of using this SDK, as well as to qualify for that track, or if you wanted to build a GameFi application as well. The point is, either way, if you're talking about building a subnet, you can build it directly without having a sort of go-between step of building a library that's going to be easy to use. But at the end of the day, some part of your project is going to be something that is abstractable and usable by other projects. It's just a question of whether or not you architect it in that way. So maybe, this could be something where you just build directly your GameFi application, but this is a month-long hackathon. So one thing that could be very cool to extract out of that is, all right, what is shareable about that? I just answered that live, so I guess I won't type a response there.
Yeah, cool. Thanks, Aaron, for really the in-depth sharing and at the same time providing a lot of context in terms of some of the ideas that people can actually explore when it comes to the hackathon. And yes, I think just kind of keep things really simple as part of the project submission. And I think that's essentially where we're kind of coming from for the hackathon piece itself. So thank you, Aaron, for taking time to share a lot in details what about subnets. And I believe that everyone here today has the opportunity to really kind of deep dive into their component and really to understand a little bit better as well. Other than that, we have kind of concluded today's session essentially. And for those who have actually taken time to participate in today's session, really thank you. And I hope that, it will be something that you've kind of taken away and to be able to put into practice for the hackathon itself for the next 3.5 weeks. So next week, we're going to have last session for the workshops. Over there's actually 2 main topics, which is essentially on top 5 vulnerabilities and exploits, and also security products, which are both done by one of the sponsors, Certic. Other than that, do kind of hang tight and keep out for announcements on the Discord channel. If you are not already on it, do join them. You have the access via the participants guide. Or the moment you have actually registered as well. So just a quick reminder for everyone that in order to qualify for the hackathon prizes, please ensure that every member within your team, and even if you're hacking solo, to actually be registered for the hackathon. You can find all the information on AngelHack social, and similarly going to be on the chat box as well. Other than that, if you have any questions about Avalanche, you can actually find Aaron and Gabriel on the hackathon Discord as well. They are actually on there to answer any of the questions with regards to the utility of any of the tools that Avalanche actually provides, how to kind of integrate them with any of the ideas as well. Both of them will actually be on Discord channel to help answer any of their questions. Other than that, thank you everyone for taking time today. Once again, thank you, Gabriel. Thank you, Aaron, for taking time pretty early on your side. I really appreciate it as well. And thank you all. Have a good one. Bye-bye.